Okay.
Thank you all for dealing with the endless technological things that we've all been dealing with for the last year. So you'd think it would have gotten easier by now.
So I can't share yet, Carrie. You have to make me a host again. Okay. We are back. Let me. So hopefully you all can see my screen, yeah, and the little laser pointer, and clearly you're probably seeing on the bottom. I tried to let it activate subtitles for anybody who might need them, but it says it's not currently available. So sorry about that. I'm going to be talking with you all today about the role that the environment plays in accelerating material failure. As Martin said, I am a material scientist. I'm in the Department of Material Science and Engineering here at the Ohio State University. And my kind of field of expertise, my research area, is really in how the environment promotes material failure. So that's what we're going to be focusing on here today. And to do that in kind of a fun way that hopefully won't involve too much background material science knowledge being necessary, we're going to talk a little bit about real world failure examples that largely involve the role of the environment, and then how kind of in one case study, how the research that my group does is addressing that kind of problem area, and it's specifically for naval ships. All right, so the first thing I really wanted to do though is to show you all or share with you all kind of where I work and the environment that I'm working in, since I'm not there and you're not here, so you can't see here either. I work within the Fontana Corrosion Center at Ohio State, so that is one of the preeminent research centers within the U.S. There's like 2 at universities within the U.S. It's one of the big 2. And there we have, as you can see, 5 different faculty members, myself obviously being right here. And then there are 4 others who do research. The last 2 here are part-time faculty here in the Department of Material Science. And our goal within the Fontana Corrosion Center is really to utilize both experimental and computational. The fellow right here uses computational approaches specifically to understand and quantify environmental degradation of materials. And this is important for many different applications and technologies. So basically, pretty much anything we utilize a material in, specifically for most of us, it's metals, you can have, or you will have, an environment that material is used in. Even when you think of like space applications, that satellite, that whatever, had to get to space, and in the process of getting there, interacted with an environment that can and has caused corrosion issues. So we deal with aerospace and automotive environments quite a lot. I also have research in energy, so nuclear waste storage canisters, those at power plants are being utilized for longer and longer amounts of time. And because they're being used beyond their design life, there is concern that we're getting corrosion issues that could cause a containment issue. So actually the research you see, the pictures right here, are from corrosion research that we're doing on material used for nuclear waste storage. Microelectronics, a lot of issues can come up with corrosion there. There's a lot of bio-related research. We don't do any here at Ohio State currently, but there's a lot of issues with implant corrosion, implant failure, and then toxicity because of metal ion release. At the end of the talk, I'll tell you a cool application. So lots of what I do is about how corrosion is really evil and bad, but corrosion can also do really great things. And I will show you 2 bio-related great things that it does. So it's used for good quite a lot as well. And then infrastructure. So obviously we have a lot of infrastructure issues here in the US, and a lot of that is corrosion related. So the work that we do impacts most everything that we do or we utilize in our real lives. So as I alluded to, here are a lot of different kind of pictures and images of the corrosion work being done here. There is stuff on inhibition of corrosion, things like the ability of paints and coatings to protect, which would be like up here, and understanding coating degradation, different environmental effects. So if you have H2S or you have CO2 in your environment, what might that do and how might that change corrosion behavior? We look at different material systems being coupled together. So this is an example of research that we have ongoing here at Ohio State, looking at different ways to join materials for automotive applications. So as we look to lightweight vehicles to make a more sustainable product, so you don't use as much fuel, you also have more reliability over the long term and its ability to kind of withstand the effect of the environment. There's a lot of research going on different joining technologies. And as you join different materials together, you get serious corrosion issues. So we're doing a lot of research around that as well. Specifically, what's related to what I'm going to talk to you about today and what my research group primarily focuses on, the thing that kind of sets me apart from the other peoples at the top, besides my gender of that first slide, is the fact that I do an incorporation of two things. So I look at how the environment as well as mechanical stresses combined to make the situation even more difficult, essentially. So I incorporate, and when you see physical metallurgy, that basically means what is made, how the metal's made up, what physically is present. It looks like just a shiny surface, but it's really a lot more than that if you take a microscope and look at it. And so looking at corrosion, the actual makeup of the material itself, and then mechanics to really address environmental acceleration to fracture. So if we're having mechanical stressing, which most engineered structures we utilize have mechanical stresses either overtly present or they may be kind of residual within the material itself from how it was fabricated. But how does that continue to accelerate failure? So things that I do are trying to understand atmospheric corrosion effects on environment-assisted cracking. So typically, when we do experiments in the past, it's usually under full immersion. So we're looking at things that would be like immersed in the ocean, and an airplane would never be that unless you have other problems besides corrosion. So we're trying to advance our kind of research community's ability to properly and accurately take into account ozone, UV, humidity with salt, because you get little droplets on a surface. And what does that do? We also do a lot of research understanding kind of how alloy chemistry and thermomechanical processing affects. So the way you make a metal, how might that affect its ability to withstand corrosion and environment-assisted cracking? Martin kind of mentioned the NSF Career Award proposal that I had gotten, and that looks at this bullet point here, the way that something's made, how can that change what's physically present in the material and how that might then alter the performance. And we also look at kind of measuring and building a ability to measure what's actually in a cracked tip. So understanding what's actually going on at the site we care about, which is a very small site and hard to actually do. And then we also do some research in inhibiting environment-assisted cracking. And these are just all pictures of different results and things like that. So that's kind of what we do. Now, I want to give you a bit of an introduction to what is corrosion as well as what is environment-assisted cracking. So Martin kind of implied that y'all love science, work in science, right? But science is a massively broad field. And typically people think of corrosion as just rust, right? Like, okay, I have a rusty wheel on my bicycle, I need to change it out. Ooh, exciting, right? That's not very exciting. I also don't find that very exciting. So what really is corrosion and why do I find it exciting? I want to kind of give you a bit of a flavor of that before we dive into kind of failure. So here are three different definitions of what corrosion is, and they're all three slightly different. And after this, I'll give you the definition that I have. It's slightly more specific, and I give it to undergrads so they can really hopefully understand what corrosion really is. So these two here are people who have written kind of massive textbooks in the field of corrosion. Kind of McCafferty says it's destructive attack of a metal by its reaction with the environment. Fontana, who was at Ohio State, which is why we have the Fontana Corrosion Center, the building I work in my labs in is also the Fontana Laboratories. He said it's deterioration of material because of reaction with the environment. So clearly there's an environment and there's a reaction going on here, right? The US Department of Defense, which you might not think they would care about the definition of corrosion, but they do. There's actually an Undersecretary for Defense that's totally in charge of corrosion and corrosion related issues, because corrosion is a massive money sink for the military. A lot of their assets corrode and they have to replace them far more frequently than they would want. So they have an Undersecretary of Defense just for corrosion. And their definition on their website is the deterioration of material or its properties due to the reaction of that material with its chemical environment. And if you care to know more about corrosion and what the Department of Defense thinks, their website is here. There's like a whole thing. They fund research, all kinds of stuff. For me, in my definition, and how I teach our undergrads here is I say it's deterioration of a conductive material, and it has to be conductive. So something that is completely non-conductive will not undergo corrosion. And the reason why will become apparent in a second. Typically, when we think about corrosion, we think about metals. Although I will tell you it's not just metals. Glasses can in fact corrode. It just takes tens of thousands of years to do so because the conductivity is so low. For metals, it can corrode very much so in our lifetimes, which is why the majority of corrosion research sits there. So it's a deterioration of a conductive material through interaction with the environment in a process that involves electrochemical reactions. And electrochemical reactions, for people that haven't thought about chemistry in many, many moons, means it's a chemical reaction that has the exchange of electrons. So there's a paired, you can think of redox reactions, might have been how you've heard it before, right? You have these coupled oxidation and reduction reactions in which you are exchanging electrons between species. And that's why it needs to be conductive. You have to exchange electrons. And we'll see these paired reactions in a hot second. So some examples that you all might know and see every day of corrosion are things like rusting of an iron pipe or rusting of any kind of iron, gates or fencing or whatever that you all have in Florida. In Florida, corrosion of iron is very common. Patina on a bronze statue. So when you see the bronze statue have that like cool color, that is a result of corrosion. Cracking of heat exchanger tubing in a nuclear power plant. A lot of the times that is due to corrosion and corrosion related processes. Anytime you see peeling or bubbling up of paint, typically that is due to corrosion happening underneath the surface and the subsequent reactions that release gas that causes that paint to bubble up. If you ever have your stainless steel utensils and they have little black dots on them, a lot of times that's due to pitting. So you're getting kind of contamination or pitting resulting from just basically the contamination that's in everyday air. It might be contamination from your cleaning products, but pitting of stainless steel kind of has these little black dots all over it. And then aluminum alloys that are used on aircraft, a majority of their cracking issues, and I'll show you this case study in a minute that kind of shows this to you. The majority of the cracking issues there are related to the environment and to corrosion processes. So note that these pictures down here are all images of corrosion, right? So not the way that you'd see it if you're kind of walking down the street, but when we cut it open and really look at it, corrosion itself can take a lot of different looks. We have things like pitting corrosion, where you're just kind of, making a pit or a goiter kind of in your surface. Intergranular corrosion, it's very specific sites. We call them grain boundaries. You don't necessarily need to know what that means, but it looks like this, where you have very specific sites of corrosion attack through your material. And this can be very egregious for mechanical properties. Exfoliation is basically intergranular corrosion, but it's in a material where it kind of flakes up, like it's a severe exfoliation of your skin, like the book just page is opening up. You actually can see this sometimes in kind of near seacoast environments on a lot of materials. So if you look around and you see your material kind of flaking away, it's exfoliation corrosion. And then crevice corrosion is something that's very common. So this came from a material where there was a bolt that was down, and you can see that the bolt head underneath of it, there was attack because of crevice corrosion. So anytime you have a small, tight space where some electrolyte can get in or some environment can get in, you can get accelerated corrosion there as well. So these are just different images of how corrosion can look, and it can look different depending on the material system and the environment that you're in. Note that there are other forms of wear, right? Like you might know about erosion or galling or wear. Those are not corrosion because they do not involve electrochemical reactions. So specifically, the field of science that I am in looks at the role of these electrochemical reactions and their ability to degrade a material's ability to perform its job. So in case you kind of don't remember, don't know what electrochemical reactions are, which is totally possible, basically these are what we call redox reactions. They're two half-cell reactions. So for iron corroding in hydrochloric acid, for example, so that would be a total reaction that you see here. The thing that you would look up in a textbook, it would tell you this, right? And what's actually happening here is not, magically iron just goes and grabs the chloride and pairs up and leaves the hydrogen to be. There are two different things happening simultaneously here. And one is called an oxidation reaction, one is called a reduction reaction. And that's how you think of them as chemists. If you are an electrochemist or a corrosion person, we call them different things called anodic and cathodic reactions because everybody likes just to make life difficult. So we call them something different. The anodic reaction is basically means oxidation reaction, or you're losing the electron. So for corrosion specifically, that anodic reaction, the oxidation reaction, where you lose an electron, it occurs on your metal, right? So my metal is losing electrons. And when it does that, the metal atom will become an ion. And it can't be an ion still in the metal state, right? So it's going to come out. We're actually physically losing an atom from the material itself, and it's becoming an ion just freely floating in my electrolyte. So little diagram down here, this is now for aluminum and water, but you can kind of see that, right? So I have my metal, technically a metal. We think of it as being this kind of sea of metal ions, and all of the electrons in the valence state can kind of flow freely around it. And so here is my metal, my aluminum atom sitting here. It has its valence state so that you can see what it's going to become, right? So the H plus in my water, right, reacts with that aluminum ion, and this paired reaction will occur, although here it will be aluminum now, right? And the aluminum 3+ ion will float out into the water, be on its own, and the 3 electrons are going to come to H+ atoms that are adsorbed on the surface and be able to basically make adsorbed hydrogen. So you get hydrogen generated. Note, depending on the cathodic reaction, you can also make OH-. There are different reactions that can occur. For iron and hydrochloric acid, it is this one here, right? So we get one reaction losing electrons, and that reaction for corrosion specifically means it's coming from the metal state and making an ion. Those electrons can't just, hang out with nowhere to go. They go to this cathodic reaction. That cathodic reaction is consuming those electrons. So here in the example, H+ in the water is taking up the 2 electrons to make adsorbed hydrogen. And typically that hydrogen will bubble off. It'll combine with another hydrogen that's adsorbed and then bubble off and go away. So that's kind of the skinny of what's happening in the one slide guide to what actually is happening with corrosion in these electrochemical reactions. For corrosion to actually occur, you need to have a susceptible material. And 2 examples of susceptible materials are silver and magnesium, right? You have to have a susceptible material, but the environment that it's in is also important. So not every environment is sufficiently aggressive to cause corrosion. So for these same 2 examples, the air that we're all standing in right now is enough to cause a lot of magnesium to corrode, but silver not so much, right? So we make our jewelry from silver. It would corrode if I put it into a sufficiently aggressive environment, but air is not that. You also need to have the elements of a corrosion cell. And I just tell you this because this is something that is utilized all of the time in corrosion protection. So an anodic reaction site and an anodic reaction, right? So you need to have a place for that metal ion to come from. And you need a cathodic reaction site and a cathodic reaction. And they don't happen at the same atomic site. You need an electrically conductive pathway, right? We need these electrons to flow, which is why it's electrochemical reactions that are important here. Then you also need an electrolyte present for the ions to flow away from your surface. If they can't flow away from the surface, you can actually inhibit corrosion. So typically when we think about inhibiting corrosion, we're actually accessing these right here. So we're either covering up with a paint or something, the surface, so the electrolyte can't touch it. We might also be kind of killing the conductive pathway as well. When you have 2 materials that are touching each other, you can kill a conductive pathway and stop corrosion from happening. And note, really what corrosion is just a return to equilibrium. So when we make metals that we utilize every day, steel, so from the iron state, right? The iron-based alloy, which would be a steel, and any aluminum-based alloy, we're actually digging that first out of the ground, right? So you think about iron ore, Aluminum is also an ore. It comes out, we call it bauxite. But when we dig it out of the ground, it's actually an iron oxide or an aluminum oxide. It is not in its metallic state. In fact, the company I used to work for, Alcoa, that Martin mentioned, they are one of the first companies and the first one in the United States who developed a patent for making aluminum cheaply. So aluminum, back in like Napoleon's time, aluminum was really expensive. So you would get like very rich people would have rattles made of aluminum. Now aluminum is very cheap because a process was found to be able to make that aluminum and separate the aluminum from the oxygen cheaply and more readily. But all in all, right, we get it out with this kind of iron oxide, aluminum oxide. We put a lot of energy and a lot of money into making it a metal to make our cars, to make our pipelines, to make our planes, when the thermodynamic equilibrium state is what we got it in, right? So we put a lot of energy and a lot of money into making a metallic material that all it really wants to do is go back to its thermodynamically stable iron oxide or aluminum oxide. And when you see rust, that's what it is. It's iron oxide, iron that is returned to its thermodynamically stable state. So basically, what corrosion scientists are really trying to do, people like me, is we've put energy so that we have engineered structures into making metal, and we want to keep it there as long as possible, right? So we are trying to sustainably use it for as long as we can so that we're not having to go back and make more material and put back in more energy and back in more energy. So it's really kind of a sustainability study in a sense. We're trying to conserve the energy that we've put into this material for as long as we can. All right, so with that, we're now going to get into kind of the fun stuff. It's most of the introduction you need. The only rest of the introduction is, what is this environment-assisted cracking term? So many structural materials, aluminum, titanium, steel, magnesium, nickel, they can go on and on, right? The environment around us is enough to cause corrosion. So even kind of wet winter roads, that's what I think about up here in Ohio. Salt water is what you all think about in Florida. Both of those are enough to cause corrosion of any of these materials up here. That corrosion, just like you saw before, will look kind of like this. But what it also can do, particularly in these two situations, is cause cracks to initiate and grow when you don't normally expect them to. So when we make a thing like an airplane or a car, right, we bake into that as engineers assumptions on when that's going to fail. And there's certain tests that people do to know when it's going to fail and make sure you're operating safely. But as we know, and as I'll show you in a second here, there are accidents that happen. And those accidents happen because a lot of the time the environment causes those cracks to grow and initiate when you don't expect them to. And what's really happening is a brittle fracture process. So typically, as material scientists or mechanical engineers, you want to think called a ductile fracture process. What that means is you physically see the material start to change. You can see a shape change before something breaks. Brittle fracture, you don't see that change. And when you have corrosion processes, it induces this brittle fracture process. And the main issues that happen here is that a corrosion site itself can basically make the stress more concentrated. So the stress is felt more severely near corrosion, and that can cause a crack to initiate, and you wouldn't normally expect it to. It'll initiate faster, and a crack will grow at rates much faster than you expect. So when you aren't anticipating the impact of the environment, failure can happen when you normally would never get it doing so in the first place. So why do these failures occur? We're going to look at a few case studies here, and then we'll talk about some research. So the first case study is aerospace. And the very first aerospace example I'm going to give you is actually not necessarily environment related, but I give it to you because it's something really neat. And if you go onto your PBS local station, likely right now, I know mine carries it. I think they all do right now. There's a really cool example where they talk about this. So it's a neat example that we'll play off of in a second here. So if you've ever sat in an airplane and you wonder why the windows themselves are ovals instead of squares, like, in our house we have square windows, but in an airplane we have circle windows or oval windows. It's not because whomever designs the aircraft just loves ovals. There's a real reason for that. And the real reason for that comes from this de Havilland comet. So the de Havilland comet, it was a British airline manufacturer, and it was actually the first commercial flight that went kind of transatlantic that would go all over the world. So they made the first kind of commercial jetliner that could really travel long distances. And this first commercial jetliner, its first A test flight was in July of 1949. It had multiple test flights, and then its first commercial flight with human beings on it going on vacation or wherever. I believe they were going from Rome to somewhere. I can't remember where they're going, but they're leaving from Rome. And what happened? They got failure that occurred. So basically this flight, it leaves from Rome and it ends up breaking up. So this is not the very first flight. The first flight was in 1952. 2 years later, 1954, in January, this flight was leaving Rome and then crashed over the Mediterranean Sea and completely broke apart. Every passenger on that flight was lost. And then again in 1954, so that was January, and in April of 1954, another plane broke up over the Mediterranean Sea and all passengers and crew were lost there again. So basically, this jetliner has had, it's around 1,000-ish total flights that each of these individual planes had made. And all of a sudden, after about 1,000 or so flights, these jetliners are just completely busting apart. Well, it turns out, right, they first made square windows on these planes, and these square windows were failing. You can see here is in the fuselage, like a big crack that has occurred within it, right? These square windows that exist, basically right there, there's also some rivets that are put in to hold different parts of the plane together and put the rib structure on it. And those square windows, along with those fastener holes that are very nearby, caused a fatigue issue in this aircraft. So fatigue means basically you load something and then you kind of let it go. I put stress on it and let it go. So every time that fuselage plane would pressurize to go up into flight, and then it would depressurize when it came back down, that's a fatigue cycle. And about 1,000 of those was enough to cause this plane to just break apart. And no one had really kind of considered that being the case. In fact, if you kind of go back and read through some of the testimonies and different documents you can find about these crashes, what you'll find is other aerospace companies like Boeing basically said they would have done the same thing and made a square window. They did not at that time in the 1940s and 50s realize that this corner that we know now, and that I teach all the time in my classes, is really bad because it concentrates stress and can promote a fatigue failure. Now I give you this example. One, as I said, if you go to PBS and you do Secrets of Royal Travel, the Queen of England used to fly on these Hallaband comets. And so they talk about it in episode 2. And more, they talk about it from the sense of it being a catastrophe that, they didn't, here she is flying on this plane. Luckily, none of hers went down, but it could have just as well as anybody else's because the Royal Air Force used them. So it's a really cool little segment on material failure that you can watch. So that was in the 1950s, right? Early 1950s. 1988, we're still getting problems of this. And I'll show you a problem that's happening like today as well. So this is an Aloha Airlines flight. So this was like pedal jumpers that go between the Hawaiian Islands. They fly low. And when you fly low and you're in a warm, salt-containing environment like Hawaii or Florida, there's a lot more salt spray that comes up. So now you're getting environment-assisted cracking issues more prevalently. So what happened here is that the fuselage frame, you can see this whole section of the plane is physically missing, and that occurred in air. So essentially this thing is flying and a crack ripped through one whole bay of the aircraft, taking that section off completely. This occurred again, as I said, in 1988. Luckily, everybody was kind of strapped into their seats, save one flight attendant who was walking the cabin for whatever reason. She did lose her life, but everyone else was strapped in and completely safe. And what the cause here is that when next time you fly, look on the aircraft and you'll see these bays of the fuselage. And what they actually do is they put them together, and this is called a lap joint, where the fuselage section of one part kind of overlaps with the other, and then they rivet it together to hold the whole plane together. And in there, you can leak in electrolyte, leak in environment, salt water, whatever, right? So salt spray that's coming up. Even the environment here in Ohio is enough to get an electrolyte in there, right? So you get this electrolyte in between your lap joints, and corrosion can occur. And when corrosion occurs with this continued fuselage pressurization, just like we saw in the last thing, that corrosion can concentrate stresses and cause a fatigue failure. And that's exactly what happened here. And in fact, if you go back and look at different kind of failure reports that are published, you can see that some of those reports say that it was noted that the Aloha Airlines personnel actually saw corrosion in the lap joints when they were walking around the planes and doing inspections. But they didn't at all in the 1980s consider the fact that that type of damage would be critical to the integrity of the lap joint and that it would kill overall kind of airplane worthiness. So this failure was actually quite catastrophic, and it got a lot of attention towards this kind of aging aircraft and the effect of corrosion on material failure. In fact, so doing my PhD work in the early 2000s, this kind of after effects of this crash actually led to the funding that I had for my PhD as well. So, and it's a lot of the reason why the military spends a lot of money on corrosion issues because of this specific failure and the light that it brought to the impact of corrosion on material failure and metal failure in aircraft. You can see some of that actually shown through some data here. So the military, so this is a guy named Greg Scholes, and he works for the military. And what he does is every so often goes and takes apart every single Air Force asset. So every plane that the Air Force has, I don't know how often, not terribly often, but they literally take everything apart. And they go and they look to say, hey, where do I see a problem? This problem could be small, or it could be something that really would in fact cause a serious failure to occur, but they're looking for any and all damage. And then they quantify how that damage got there, right? And so you can see number of findings based on the type of damage, and there's also, this part had no damage. And you can see there's things like mechanical damage or material defects. So mechanical damage might be, a rock hit the plane and caused a scratch or a dent or something. You can also get mechanical damage when you like rivet something on and the person doing it misses and the drill bit hits something. So there's mechanical damage, but the majority of damages sites they found are related to kind of what they call operational usage, and a lot of them related to corrosion. So you can see bore corrosion, regular corrosion, exfoliation corrosion, that's that flaking up I showed you, intergranular. You can see corrosion fatigue, stress corrosion cracking. These two are environment-assisted cracking related. You also can see fatigue here, and in a second I'll comment on that. And when they looked at any damage that was cracking related, so fatigue, stress corrosion cracking, corrosion fatigue, any kind of crack that was emanating from that damage, they went back and said, what's that damage initiating feature? What's the thing that caused that crack to start? 80% of the time it was a corrosion pit, right? So if a corrosion pit started it, the environment didn't go away. So a lot of these fatigue failures, what they call just fatigue, technically would be classified into environment-assisted cracking and corrosion fatigue because of the fact that a corrosion pit started it. The other thing to kind of note is this is a different report of commercial aircraft and what caused either an engineering component or the actual aircraft to fail. Failure not necessarily being falling out of the sky, right? Like those first two examples. This would be something that would cause it to be decommissioned for repair. And you can see within that all of the red is related to corrosion, and the gray here is fatigue. And if we count the actual numbers, right, for red, it's 35% and 23% of the engineering and the aircraft components are failed because of corrosion. If we count in fatigue, like I just showed you up here, right? If a pit is the initiator, likely 80% of the time, I'm going to count 80% of this fatigue to be, the 80% of this fatigue to be qualified as corrosion related. And so you were looking at 60 to 78% of all failures are related to corrosion in the first place. So for aerospace structures, and we could do this case study for a lot of different industry sectors, we find that corrosion is a huge player in why something fails and why we have to stop working with that engineered component. Just to show you the relevance, right? So we said 1940s and 50s we had a failure, maybe not necessarily corrosion, but it could have been partially driven by that. It wasn't looked at the time. Then we said the 1980s, we still got a problem, right? This is something from 2019, where and you can still see some reports on this in kind of the news if you want to go looking for it. The Airbus A380 super jumbo jet has had a lot of wing cracking issues, and a lot of those wing cracking issues, I think the litigation has just been settled recently, but there's a lot of litigation on what the role of the environment is because it is something, and whose fault was it because the environment played a role in this. So, right, even today, we still have issues of environment-assisted cracking in aircraft. And it's not, corrosion is not just related to aircraft. I'm sure everybody has heard of kind of the Flint, Michigan water crisis, right? And there was definitely a corrosion-related problem. So what happened here was that Flint decided to switch their water source. They went from being the Detroit water source to having their own out of the Flint River. And when they made that choice to change, they decided they were going to save some money and not use as much corrosion inhibitors, because they thought that their personal river was just less corrosion susceptible. So they decided to take out the corrosion inhibitors. They also made some other changes and poor decisions in the end that led to substantial corrosion of lead-based piping in Flint, which led to lead in the water. And lead is a contaminant that is not good for your body. So if you're drinking it, it can lead to some serious mental health issues and some other issues. So, and which most parents will know, right? Every little kid gets lead tested because of lead-based paints, right? But you also get lead in your water. And so this huge crisis was a huge corrosion failure and an oversight of people paying attention to the likelihood of corrosion to occur when they changed a water source. And you can see in here, right, the supply had, this is from NPR, the supply lines had sustained major corrosion causing, and their lead-based pipes causing that lead to leach out into the water, which caused a public health crisis. The last little failure I'm going to show you, and then I'll give you a kind of a research related tangent, is with Navy ships. So the US Navy, as well as the British Navy, most navies, right, to make their ships faster, which then will so they'll make them lighter, you can make them faster. To make them faster, they put a lot of the superstructure and deck structure, these two ships are good examples of it, are made of aluminum. So historically, ships are made of steel, but if you want to go fast, steel is far heavier than aluminum, and you need to switch that lower density material. And so aluminum has been used a lot on modern ships to make them fast. So littoral combat ship, this joint high-speed vessel, anything that's like a ship to shore, or you want to go fast, or you want to carry a lot, so you need to be lighter as well. They are making of aluminum, and a lot of it is kind of deck, hull, superstructure items. They made these out of what we say a 5000 series aluminum alloy. So this number here, what it really means is that it's got aluminum with a little bit of magnesium put into it. And this tells you kind of what processing you've done afterwards. But all in all you need to know is aluminum with a little bit of magnesium. And that little bit of magnesium is meant to be what we call in solid solution. So if you think about like sweet tea that doesn't have too much sugar in it, you don't see the sugar, right? It's kind of just combined within the water. It doesn't do anything special, just floats around all over the place. That's normally how the magnesium is supposed to sit with the aluminum. And when it does that, corrosion properties are fabulous. But what they didn't account for, and what you can see on this is a ship deck. What they didn't account for were these fact that the sun is going to beat down, right? The sun's beating down on this ship, the sun's beating down on that ship, particularly when you're in warmer environments. And that heat actually causes the magnesium to what we call precipitate out, meaning the magnesium is actually sitting in a separate phase all on its own. And when that happens, it causes a lot more corrosion to occur and stress corrosion cracking and corrosion fatigue to occur. So a lot of the superstructures and the decks within a lot of these ships have experienced some major cracking issues, as you can see here. And that major cracking is related to the effect of the environment, corrosion, plus the mechanical load that's on these ship decks, right? So a lot of these decks actually have, like here, right? You have a deck that you could land a helicopter on, or you can land an airplane on. A lot of these aluminum alloys are used for what they call a lift elevator for an aircraft. So the aircraft sits on it, and then it lifts it up to the deck to take off. So these aluminum plates on a deck are experiencing quite substantial loads. In addition, the wave action, if it's something that's sitting on a superstructure, that wave action, the bending motion that the ship goes through, causes a force to be applied, and a fatigue force, in fact, on that ship. And so that's what's causing kind of these cracks to occur. The sun exposure changing the physical metallurgy of the material, and then the stress applied is causing these cracks. So there's a lot of research that's been going on since about the early 2000s up until today to try and figure out why is this happening and how do we combat it. Some of that research funding was in my department, in my research group. So I'm going to tell you a little bit about that. Because all of these problems, research does address them, right? That's why I have my job, essentially. So all you really need to see here, right, is that there are two different aluminum magnesium alloys we looked at. Depending on the amount of magnesium you add in, that number changes. And you can see actual pictures of what that material looks like in an optical microscope here. So we take and we cut the material, we polish it, and we etch it so that you can see different features and take a picture. So you can see, right, it doesn't all look the same, right? There's a matrix, there are these things called the grain boundaries that are light in these pictures. And there's also other little phases present, kind of like an oatmeal cookie, right? You have your oatmeal and you have little raisins in there. The raisins are different phases. So this is what it really looks like in a sense, not in an SEM, but just optical microscope. The numbers down here, I'm showing you these little curves. This is called a degree of sensitization. So how much that material is baked by the sun, you can think of it. To do research, we bake it in an oven. And the higher that this number gets, the worse the corrosion properties, the worse the cracking properties are. This is how long at a certain temperature that thing was baked. And the only reason I point this out is these numbers are going to appear on the next graph for you. The research that we did in my group was looking at corrosion fatigue resistance. So how we do these types of experiments, and you saw little kind of pictures on that like second or third slide, right? For this, for these naval applications, what we did in this specific case is we have a plexiglass cell. It sits around a sample, right? And that sample is then put into a loading frame. So we can then pull on it with fatigue loads. So I can pull on it really hard and then pull in a little bit, and fatigue kind of cycle that load up and down, up and down. We cut our sample out. It looks like this. It's got this notch, this like cut in it, so we can force the crack to go right here. And then we use a technique called direct current potential difference, which we apply a current, a constant current across our sample to actually physically measure how fast that crack can grow. And we can actually measure a change in crack length that's less than 10 microns, and we can measure that happening. When we apply that constant current, we basically use Ohm's law, right? V equals IR, and we have a constant current. When we grow a crack, it will cause a resistance change. And so we measure the voltage out here, right in the crack mouth. We can measure voltage changes and then translate that voltage change to the resistance change, and we can then translate into a crack length change through certain equations that are calibrated based on your sample type. So we put this vat of electrolyte around it. Note, we can also do, people have done research where you're spraying salt on it, so it's like a superstructure instead of, the boat part under the water. There's a lot of different environments we can do this in. But what we did is in full immersion in electrolyte. And our goal here was to say, okay, if I want to change my loading frequency, I want to load it really fast, like they do typically in labs, or I want to load it really slowly, like I would for a wave action. What happens and how is that different? And how does that effect of baking it in the sun alter what happens? So we can see some of that here. Here is how fast a crack will grow as we measure and how fast it's physically loaded. So, right, 10 hertz, 10 cycles a second, I'm pulling on it really fast, which is what you want to do in a lab to be fast, but not really replicative of what that ship is seeing from the wind and wave action. That's the most egregious action causing the cracking to occur per the Navy, right? So we said, okay, let's load it fast and let's also go really slow. Things that only university people want to do because it takes a really long time, right? When we see lab air, no environment, you get a crack growth rate that's here. You get an order of magnitude acceleration if you load it without any sun exposure, right? And 3.5 weight % sodium chloride solution. So just having the environment there has caused a crack to grow an order of magnitude faster. Now, what we really cared about was not just what does the environment do, because this was not necessarily a shocker. We want to know now if I accelerate or simulate that baking in the sun to change this number here and make it higher, effectively, what is that going to do? And these numbers here for people that don't do any mechanical loading, just tell you how we mechanically loaded it, how aggressive we were mechanically. Okay, so what we see here, and this is for just one of those aluminum magnesium alloys we looked at, right here is that 10 hertz. Right here is 1 Hertz, and I'll go back. Right here is 1 Hertz, right? The data for lab air is no longer on this plot because it's sitting down here. Here is that data with very little, we call sensitization or essential baking, right? Very little is down here. You see a frequency independence, just like you saw up here, right? So it doesn't matter. I can load it fast, I can load it slow. My crack growth rate's the same, which is what you normally want because people tend to estimate properties fast in a lab, and then they want to apply it to low frequencies to model how quickly damage will occur, right? That's what you want to see. But as we slowly start to kind of bake our material, expose it to 100 degrees, 175 degrees Celsius here, we did another study with 100 degrees Celsius. There's some other people that do 60. The lower you go in temperature, the longer it takes. And what you see is as you raise that number, right, crack growth rates don't do a whole lot initially. In a middle range, they start to increase, but we're still frequency independent. But when you get really sensitized, these really high degree of sensitization values, meaning I've changed my metallurgy quite a lot in a not great way for corrosion, you see that we get this very steep frequency dependence. In fact, the crack growth rate is increasing an order of magnitude for every order of magnitude decrease in frequency. This is more close to what a naval operational frequency would be. And what we see here is that the crack growth rate is 3 orders of magnitude accelerated over what it would be had I never baked it at all. So we're seeing severe, what we would consider severe acceleration and damage accumulation because of the fact that that material was exposed to temperatures that are slightly elevated from room temperature. And in fact, you can get, so these values in the lab, we can get them in, depending on the temperature you use, in about 30 days or so. In Hawaii, they can reach these values. They had a ship sitting out in Hawaii just to see what would happen. And they saw these values in about 10 years. In about 10 years, a ship would experience theoretically 3 orders of magnitude acceleration in its ability to grow a crack. And so this is kind of a big deal and was a big finding for us to say, hey, you know, you do have a really egregious effect of sensitization on your corrosion fatigue properties and likely a cause for some of these cracks that you see. So before we end, just to give you some happy notes, right? My research tends to talk about all the bad things that happen, and I'm naturally more of an optimistic person, so I always like to end things on a happy note. So corrosion isn't always bad. I'm going to give you 2 examples of some cool things that corrosion does. Both are bio-related to kind of make them more personable to everybody. So there are metals like magnesium and copper that are not toxic to your body at all. Magnesium, in fact, is being utilized in kind of modern times as a bioabsorbable implant. So there are many reasons why you get a metal implant and you don't want it to stay, right? If your hip's replaced, you want that to stay. But if you broke a bone and you just need to mend for it until that bone can heal itself, you just need to mend it and put a screw in, you can actually implant a magnesium alloy that will corrode in a very specific amount of time. So you can tailor the corrosion properties based on what you put in it and how you process that magnesium alloy. And when you do that, you actually can cause it to corrode once you, in a timeline that you believe that the bone will have healed in. So these are examples of screws that are magnesium based that serve a temporary purpose. And then it corrodes and you basically just urinate it out, right? Over time. It doesn't corrode in a day, but it over time will corrode and your body will dispose of it properly with no harm to you, which is great because you don't have to live with a screw in your body for no good reason at all for the rest of your life. But beware, right? There are toxicity issues. You have to be mindful. You can't just go put any old screw in your body and hope it will corrode, right? As we talked about, lead causes permanent developmental delays and cognitive delays. Manganese, if it's in really high doses, can cause motor function issues. So you can put a little bit of manganese in your body and it will corrode, but you don't want too much. So when you think about materials you want to put in to corrode and be bioabsorbable, you got to be real careful what you put in. But there's a lot of research that's done to understand corrosion properties. How do you tailor them? And what kind of tolerance do you have of different metal ions in your body in order to be able to utilize this? There are also people who do research in allergies and how some of this corrosion utilizing these things might affect allergies in people. Another cool example is copper intrauterine devices. So, right, birth control measures, you can use kind of conventional pills of old, or more modern times, they use things like these copper intrauterine devices. So there's a lot of people that utilize them these days. And what they're doing, how they're actually working, is through corrosion. So you can see the copper wire wrapped around this device. This device is then inserted into the uterus. And these copper wires here will undergo corrosion in the body. And through corrosion of copper, you get these cupric ions. And these cupric ions are natural spermicides. So they basically change the mobility and the surface chemicals that facilitate kind of the breaking down of the surface barrier of an egg. They also promote kind of temporary sterility by causing inflammation of the uterine lining. So should implantation occur, the egg is going to have a really hard time attaching itself to the uterus, therefore making a non-viable pregnancy. So basically, through corrosion, you can utilize birth control measures based on how the corrosion products, cupric ions, interact with the human body. So there's a lot of cool things that corrosion does that are great for society, and it's not all bad. And with that, I can stop sharing and I can take any questions you all have.
Well, I'm just going to jump in real quick and say thank you so much for such a great presentation. You covered so many different things that are affected through corrosion, and just were able to hit on numerous topics, everything else. It's really interesting. And the nice part about having my not being screen sharing or anything else is I've pulled up numerous just Chrome tabs and said, hey, I want to look more into this and that. So maybe I'll get things started in just saying, one question I had was, a lot of the airplane cockpit windows seem to be kind of squared off, and that seems to be interesting, where you have the oval shaped passenger windows. Everything else, that might be something interesting to talk about. But I have a page full of notes of other questions I have, so I'm gonna start there and let other people come up with some ideas or questions they might have as well.
Martin, do you want me to go through and read the chat, or did you want to moderate things?
If you want to read chat, I need to pull it up myself.
Yeah, I can pull it up. Yes,
I did see a couple things pop up. If you want to just grab a few questions in there that you'd be interested in answering, or have a good way to answer quickly, would be great. And then otherwise, we'll just go through, and if there are questions that are far afield, we can address those as they go on.
Okay. So one person asked if large-scale 3D printing will help. So there's a lot of research going on right now with 3D printing or additive manufacturing, right, of metals, and trying to understand their corrosion as well as environment-assisted cracking properties. So it's very much a kind of more modern area of research happening mostly in about past 5 years or so. Corrosion research tends to lag behind things. So people tend to not want to pay for corrosion related research or to care about it until problems occur. So we tend to be the last phase of materials research. But about last 5 years, a lot of additive manufacturing research has revolved around corrosion. And mostly a lot of that is looking at porosity and will a corrosion pit ever become a more prominent player as far as failure goes than the porosity that's native there. Most of the time, 3D materials tend to be, at least from a corrosion only standpoint, a little more corrosion resistant than your native material. And that's because you can actually keep kind of the bad actors. So a lot of when I talk about physical metallurgy, the things that are actually present, if you looked at kind of the microscopy, either electron microscopy, optical microscopy of a metal, the little differences that are actually present, those are the things that cause corrosion problems, and you can keep them from appearing by 3D printing. You can kind of control your metallurgy a little bit better. Though there is very, very little that has been studied as far as corrosion fatigue, stress corrosion cracking goes. So how that will be affected, we don't necessarily know yet. There's a little bit of research, but it kind of shows variable results depending on the environment and the material system itself. So yes, 3D printing is being looked at a lot, largely because it's so easy to replace something. So if something's corroded or cracked, you can 3D print apart and put it right back in if it's something that's small. So a lot of times on ships and things are looking at 3D printing, and the Navy's funding a lot of the additive manufacturing corrosion related research. Let's see. So one person said, does vinegar, vinegar works very well to remove surface rust. Is this a form of corrosion? Yeah, so vinegar itself does cause corrosion. In fact, there is a, now when it's removing the rust, I'm not sure with the rust removal if it's a chemical or an electrochemical reaction. That would be the total qualifier in which one it is. And honestly, I don't know. But we do use vinegar actually to cause actual corrosion. There is an ASTM standard test for corrosion that they use for a lot of automotive alloys and automotive aluminum alloys. And you actually add vinegar to the spray. So you spray salt water plus vinegar on it to promote corrosion. So vinegar does cause some corrosion, and we use it in the lab to accelerate things quite often. For actual removal of surface rust, I don't know if it's chemical or electrochemical reaction, to be honest with you. Let's see. Someone know if the black dots on stainless steel products are dangerous. Well, it depends on what product. If it's on your spoon or something, no, you're not ingesting anything that's particularly terrible. If it's on, like, so some of the research I do in my group is looking at corrosion that appears on stainless steel nuclear waste canisters. Yes, it could be very dangerous there because it could be a crack initiation site that could go through wall and cause the release of radioactivity. So it just depends on what the stainless steel thing is, whether or not we would consider it dangerous. But on your utensils, no. I don't replace my utensils because I see a little black dot on there. I just get more excited that my utensil is corroded. Some person, I clean my silver annually for my synagogue. What is the best way to clean it so there will be less to clean the following year, less corrosion over the year? Oh, that is a good question that I do not know the answer to. There are people who have studied atmospheric corrosion of silver. Most of them are studying it from like an ozone and UV light perspective. I don't know what to tell you what to clean it with that would be better or worse. The best thing to do though is to keep the environment off of it. You could always put like Vaseline on it or something, but then you're gonna have to clean the Vaseline off, which is probably not fun. But I don't know what to tell you there. I have not looked at how to keep silver from tarnishing. Cover it up really well so that it doesn't get any kind of water vapor or kind of depositing water layers on it. That's what I'd say. Keep it dry as possible.
Hi, Jen, this is Carrie. Thank you
Carrie.
for a wonderful talk. I wanted to ask our participants that are still here to please indicate in the chat where you heard about it. I know there's some students from Martin's class. Let us know if you're a student or if you are, if you found it on Facebook or Meetup or a member and got an email or something. That would be really helpful for us to know how to reach people. So thank you. Well, it's a little after 7. Martin, do you want to do a follow-up and dismissal? You would?
Sure. I in general would just give a heartfelt thanks to Dr. Locke tonight for giving a great presentation. Very interesting, covered lots of bases. I know, especially for the class I teach, I like to really point out the just in numerous ways in which science touches everyday life And it's really great to see that as well, because I'm not gonna lie, I was, the other week really engrossed with the whole muon situation and the spin states, everything else. And a lot of times people have a hard time recognizing how some parts of science might reach everyday life. So thank you so much for presenting all of the ways in which your research, though very specific, is also very integrated into everyday life for us. How everything is just interconnected that way, and really appreciate that. So thank you so much, and what a great way to end our Horizon series for the spring. I hope people, if you are not currently a member, you join, and we can keep bringing you great talks like this.
Yeah, thanks for having me. It was fun. I wish I could be in Florida. It's a cold day actually in Ohio. We're having the Ohio Spring Day. I wish I could be there, but it was wonderful to be here. Thank you for having me, Martin, and for all of the students in Professor Brummer's class. I went to college with him, so I knew him when he was like you. And he knew me when I was like you too.
Well, good luck to you in your career, Jennifer. This was
Thank
excellent.
you.
Really appreciate it.
Thank you for having me.
Okay, well, I will close out this session, and everyone do take a look at our Facebook page. And if you're not a member and would like to be a little bit more involved, please consider joining as a member. Thank you. Good night.